And we are live now. Apologize for that. So what are you going to do with that action? If we're going to predict that a customer is going to churn, or a customer is going to terminate their policy or their product with you, or an employee is going to leave, if you knew that a day in advance, a week in advance, a month in advance, what would you do with that action, and how would you change that behavior? So that's everything we're kind of doing with data science. So that's the big world view, and then we're going to bring it down to kind of the small stuff today of really focusing on the algorithms and techniques. This is a reminder to myself to switch to a different slide set, so give me a moment here. I may go through a couple of different resources here, but we'll start with this one. So there's, again, probably a billion different ways that you can slice what is AI and what is machine learning and what is data science. I ascribe maybe a little more broadly to the idea that AI is a umbrella, and then data science and machine learning are under that umbrella as opposed to kind of separate. But this is some representation, and then these are kind of tools and technologies. So we obviously don't have time to learn all of this, and you guys have probably learned some of this. You've probably learned data preparation, oh my goodness, visualization, statistics. We're going to start to get into decision trees, and KNN will focus on that today. I don't know if I want to get to functions quite yet. Hold on. I thought I had one more set of slides here. Oh, here. On the other screen. Here we are. All right, really similar representation. You'll see it a lot. So what is machine learning? It's any process by which system improves their performance from experience. So throughout these slides, they kind of talk about improving performance as P, some task T, and with experience E. But this visual is used a lot to differentiate between what is machine learning versus what is a program. So a program in the computer, they're both computers. They're both computing something, doing some logic under the hood. But in traditional program, you feed it data, and you feed it a program, and then it produces some output. So that's what we've been doing. We've been writing our programs and feeding it data and feeding it a program, and we've been producing output, create this visualization, or create this function and do these tasks within this function. But in machine learning, we're actually feeding it data, and then we're feeding it outcomes. What happened in that situation? So if we look at customer churn, we're feeding it all of our customers in the past that we've had, when they churned, and when they didn't, and if they're still customers, or how long they were customers, and attributes about them. So we're feeding them all the data, but we're also feeding them outcomes. And that is machine learning. So that's the difference between kind of these two different domains. I wanted to touch on just how many different places you're going to see machine learning and data science in your day-to-day life. It is quite honestly everywhere. If you just pick up your phone, you're going to see it in everything. If your phone recommends you pictures to view for the day, you're going to see it in that. If you're going to get coffee and your coffee app is sending you notifications, the timing of what to send you and when to send it to you, that's all within the app. So these are there's a ton of different examples. I don't know if I'll go through all of them, but genomics is a really common discipline. So this is genomics over here. If we need something to navigate around on Mars, humans aren't around, humans can't help. This is really, really popular data set, by the way. This is called the MNIST data set, MNIST. And it's a data set of numbers, thousands of numbers, and they are labeled by humans of what they are. And so a really kind of introductory to neural nets problem is to see if you can predict what these numbers are. And it's hard sometimes, right? These ones are in red. Can we even say what this is? Is this a 7 or is this a 2? So it's very easy to get these things wrong. So sometimes we're asking machines to do problems that are even quite difficult for us. There's a million different things. So you use your phone, and it'll do facial recognition. That's all basically neural networks determining patterns, identifying patterns within the face, and matching that to the history of what it knows about what your face has looked like in the past, handwritten or spoken words, medical patterns, unusual credit card transactions. You guys ever get a text on your phone and it's like, we noticed this strange thing happening. Is this you? And you can validate it. Or say, no, that's not me. That's definitely fraud. So fraud is a type of model called a binary classification model. So we can talk about that. And it's a really interesting problem because it's a class imbalance problem. But that's a really common pattern. Future stock prices, it's classically a very difficult problem just due to the wide amount of noise. There's always somebody every year who says, oh, I've trained a really, really good machine learning model and I can predict the stock prices. Every year this happens. And then you go into their methodology and you sort of realize that they accidentally data snooped. So they kind of, they unknowingly cheated basically in their estimation of that. And the outcome is that it would perform terribly in the real world. So we're going to learn how not to do that in this class. How to keep with what we think our model will actually perform in the real world.
Can you emphasize a little bit more about he unknowingly cheated?
Yeah. So we can think about if we are training a model to predict the stock prices and we do a out of sample set. So we say, hey, train over all of the other stocks, but don't train over Apple or Google or Tesla. You're going to leave those out. And at the end, I'm going to give you those stocks. And then you're going to tell me how well it performs. So you're giving it unseen data that it's never seen before to evaluate on, which is good practice and good methodology. However, stock markets are time series data. So you have to be really careful because typically when some stocks go up, generally the whole market goes up, right? So the whole market kind of has a trend with it. And so even if you withhold those 3 stocks, Apple, Google, and Tesla, when you give it to your model in your test set and say, predict on this, it's actually probably going to do pretty well because it knows at that point in time, because it's a test set, it's seen how other stocks performed at that point in time. So it'll say, well, everybody else went up, so you're probably going to go up, and it would probably be right in that estimation. So you have to do something called out of sample, out of time sampling. So not only do you have to withhold time for all of your stocks, and then do out of sample in addition to that to actually get a really accurate estimate on how that's going to perform.
Thank you.
Yeah, happens all the time. You'll also see really, really common another class of problems. We touched on regression and classification, which we'll get into more today, but something we probably won't have time for in this class, more of an advanced topic, but really interesting, is something called reinforcement learning. And reinforcement learning can actually teach algorithms to play games. So if you think about Go, or chess, I guess is maybe a more common one, but Go is notoriously a really difficult game. It's very, very complex. And they said no computer would ever be able to beat a human at it because there's just a lot of complexity to it. And lo and behold, I don't know, this is some time ago now, 2017 or something to that effect, they did train a computer to beat a human at it. And I'm sure you guys have seen all the chess competitions with grandmasters playing machines and stuff like that. So that's reinforcement learning. So we will talk about that. Let me see. Autonomous cars are pretty popular and constantly in the news. So under the hood, that is all machine learning. So it's, builds on itself, and it gets more and more complicated as it turns into kind of a system eventually when we get to these vision systems. But this is really all the foundations that build to that. In fact, what we will be learning logistic regression in next week will actually be is really important to neural networks. It's kind of the foundation for how neural networks work. It's probably a gross oversimplification to say this, but it's a bunch of logistic regressions compiled together. Again, gross oversimplification. Let me see if there's anything else that. You guys ever seen? Have you seen deepfake a lot? That's what's really interesting is. I don't think this is talking about deepfake, but it reminded me of it. So what's interesting is traditionally machine learning has just been predictive. Facial recognition. Does this face match this one? Or detecting the cars here on the road. It's been focused on kind of that identification piece, but not necessarily generating new content. But as we get into what's really started to evolve is actually the generation of new content from machine learning and AI models, which is really fascinating. So if you think about large language models, ChatGPT, that's actually generating new content, and deepfake does that as well. You can basically make pictures of people that don't exist. They're not real pictures. So that's super interesting. It's a really big shift in the technology. Okay.
Do you think with, I guess, online scams and stuff like that, people probably use that?
Yeah. Oh, definitely. I would expect to see a flood of people do use the deepfake stuff to definitely do online scams. There's this people tend to, unfortunately, have a habit of targeting our elderly population. So there's a scam going on right now where they actually send you a video, and it is of your niece or your nephew asking you to send them money from jail or something to that effect.
They have it with a phone call.
Yeah.
My grandpa got one, and he was confused, but he just hung up on them because he's like, my mom was like, she didn't tell me they were going. All right.
So now they can actually make the voice sound like your niece or nephew using these technologies.
I have a customer that lost $20,000 in cash.
Oh, that's heartbreaking. That's heartbreaking. So we actually need, people to continue investing in this field because it's sort of Pandora's box, right? We can't put things back in the box. Wish we could. We can't. So we have to continue research and train cybersecurity professionals and people like yourselves, honestly, in all the fields that you work in to be experts in this knowledge to help be aware of those attacks and how we can be vulnerable from that kind of stuff. So it's critically important that we stay ahead of the game to the extent that we can here. I think I had, if we get to maybe a little more tangible, I think I just have 3 slides from this one. If we get to just a little more tangible things, all of those were really, wow, but that's so far away. What are we going to get to in this class? Some data science applications that maybe hit a little closer to home. If you use Amazon recommends new products for you to buy all the time. How do they do that? Like, how do they know what products that you would be interested in at what point in time? So that's something that we can probably start to touch on by the end of this class. Recommender systems probably warrant their own entire attention, but we can start to build our foundational knowledge and then work towards those. Predicting why patients are being readmitted is another really popular application. If you're like in the medical field, I've seen that one applied multiple times. And then I touched on it, but fraud. Fraud is, no matter what industry you're in, everybody wants to know about fraud. Who is taking advantage of their system or their, shareholders or their revenue, causing them to unnecessarily drive up prices. So fraud is a really interesting data set, and we'll definitely touch on that. Okay, I think that's it for my introduction piece. Pop back to our regular slides here. Got to say thank you to John Canny. I'm stealing his slides here, so credit to John there.
No.
No. I think this is from maybe Stanford or one of those places. So outline for this evening, we'll see what we touch on today. We probably won't get to training. We have another lecture planned to that, but we'll touch on KNN. Linear regression is going to be our main topic, and we'll touch on k-means as well. And then I'll have you apply one of these algorithms to the iris data set, and then we'll do regression on something that makes sense, probably a housing data set. Okay, so getting narrow here. Let me check the time. We're good. Getting narrow here. What is machine learning? So there's actually, I actually argue there's 4 different types of machine learning. There's supervised, unsupervised, semi-supervised, reinforcement learning, and then the list can go on. But the main 2 areas are supervised and unsupervised learning. And I touched on these briefly, but in supervised learning, we're given input X samples and output Y samples. So we're given Y labels or Y targets. So your iris data set, we're told what flower is each of those pieces of data represent. So that's called a target or a label or Y. It's typically represented as Y. Y is what we're trying to predict. And it's typically written Y equals f of X. So X being our variables that we're putting into our model. And the reason it's written Y equals f of X is because f is a function. And so our goal in the machine learning is to learn f. And we're going to talk about what is a function. What does that mean? But we want to learn f, and we want to evaluate it on new data. So how does it perform? The whole goal is not to always know what a flower is. The goal is, given something we don't know, but we have these measurements about a flower, what is it? And so under supervised learning, there's 2 main tasks, I guess, that we're going to focus on for this class. One is called classification, where we have class labels, and one is called regression, where what we're trying to predict, Y, our output variable, our target, our label, it's continuous. And so this is where linear regression will fit. Just to be confusing, logistic regression typically actually fits as a classification problem, but we'll talk about that. So classification, what does discrete mean? That means there are discrete buckets. There are individual buckets or individual labels. So you're either trying to predict, I think in the flower example, we have what, three classes? Does anybody remember?
Virginia, Sistora, what's the last one? Right?
There we go. I have to refresh my memory on that. So three labels. So we have 3 class labels, and that's typically the terminology that's used in that is class labels. And then in regression, again, it's a continuous number. It can be 1, it can be 1.1, it can be 1.137. So the
Versicolor.
there we are.
There's no way to know that. And the others.
And then we have unsupervised learning, which given only samples of X data, we have no Y. So there's no labels. All we have is information about the thing. And then we're going to try to figure out what are the relationships between these objects without having explicit labels for them. So we compute a function y equals f of x, and there's a couple of different ways to do that. We're not going to talk about any of these other ones for y is continuous. We're just going to talk about clustering. So maybe in another class or in your own learning outside, you can look at the y is continuous ones, but we're just going to talk about putting things into buckets. So sometimes you'll hear about customer segmentation. Can you take all my customers and tell me which customers are more similar to each other? Which customers look like each other? We can do clustering. We can say, yep, there's these customers over here. I don't have a label for them. I don't know what they are. We can make something up. It may be kind of nonsensical, but they all look similar to each other. And we're going to go through an example for that today. Oh, here's a whole bunch of examples on this slide. There we go. Thanks, John. Supervise. So is this image a cat or a dog or a car or a house? It's likely somebody has labeled that data set, cat, dog, car, house, like a human has sat down and labeled those things. And so that's why labels exist for that. How would a user score that restaurant? Is this email spam? Is this blob a supernova? And unsupervised, cluster some handwritten digit into 10 different classes. Or what are the 20 topics that are most popular on Twitter right now? Or find and cluster distinct accents of people at Berkeley. Oh, maybe these are Berkeley slides. That would be my guess. So here are the different techniques, or what I would maybe call algorithms. They're really algorithms. They're if you guys have ever taken, well, it's algorithms, but I'm trying to think of the exact name of the computer science class. It'll come to me. Anyways, these are actual approaches. There's rules for how these work, and we're going to start working through the first two today. So this is KNN is typically what it's referred to. It's the colloquial term, but K nearest neighbors is the full term for that. And then we'll go through linear regression as well. We'll get to logistic regression, and we'll get to random forest. We will not get to support vector machines or naive Bayes, but you guys are welcome to check those out on your own time. They are interesting. And then for unsupervised learning, we will talk a little bit about clustering. We'll do k-means clustering. We probably won't get to factor analysis or topic models, so we'll just touch on unsupervised learning. I feel like we've been pretty clear with this. I put this in here in case I wasn't being, it's not letting me click on this. Let's copy and paste. But there is a decent visual in here that I thought was useful. Let's see. So when we talk about supervised learning, you guys can read this, but I just thought this was a useful data set. We have a useful visualization. We have a labeled data set, and eventually in our methodology, we're not going to start with this today. We'll get back to methodology later, but eventually we'll split into a training data set and a test data set. We'll train our model, and then we'll test and validate our model, and then we'll predict on unlabeled data. This is our ultimate goal. We want to see how a model performs on unlabeled data. That means there's no Y value. That means there's no labels for our flowers, for example. So you can see this unlabeled data set, and we usually call that real world data, and we'll talk about what that actually means, but it usually means how well your model generalizes to unseen data. That's typically the key point there. The difference with unsupervised learning, look how much more simpler this is we take an unlabeled data set, it has no labels on it, and then we train a model, and then we identify hidden patterns. So that's pretty much all that we do with that one. We're not actually trying to, predict actual labels that go onto these things. We're just trying to put them in groups that are similar together. So when I was in, well, I'll get on that tangent later.
So that'd be like, I don't know, just put it really, really simple. where
Yeah.
it had images of animals and then we threw it in a tree, it would tell us it does not belong because it's not an animal. It says,
I'm trying to think if that fits in here.
because you're not really like, I guess you're not really predicting anything. It's
I
just telling you
think
a
in
pattern.
that case, if we had labels for pictures that and we said they were animals and you're trying to predict if it's an animal or not, I think that's your label is animal.
Okay.
Can you, so I'm getting a little lost on the identify hidden
Yeah.
patterns.
That's what I'm saying.
So what I'm hearing is it's considered hidden because you haven't classified anything or you haven't.
That's a good
that we're
point.
treating the data, but you're not like, you don't know what you're looking at yet until.
So in unsupervised learning, typically, by the way, a lot of these data sets are going to have like 10 dimensions, 20 dimensions, 50 dimensions. We're humans and we suck at visualizing things in big dimensions. So a lot of times, for examples, people just put things in 2 dimensions. So that's why you see it so much. We have an X and a, oh, in this case, we don't have a Y. So we have we have X sub 1 and we have X sub 2. So these are just 2 different features.
Do you want to switch your screen so it's bigger?
Oh,
People online? to
Yes.
see what you're drawing?
yes. How do I?
I think you should share it.
Yes. Apologize for you on the phone here. Okay. There we go. Perfect. Okay. I don't know about perfect, but good enough. So when I have to make sure that this applies to this. Yes, I think it does. When I was in college, I built a beer recommendation engine for my senior project, and so I had all these different beers, and maybe this was ABV, like the alcohol content, and maybe this one was how hoppy it was. So there's nothing I'm trying to predict here, but I have a bunch of different beers. And they have, maybe these have a lot of hops, but low ABV, these have low ABV, low hops, and this has medium hoppiness, but a higher ABV. And so in clustering, what we'll do is we'll train an algorithm, and it'll go through a series of steps, but at the end, and I'll come back to this example, but at the end maybe identifies, hey, these are 3 clusters. I can't put a label on this. I can't say, I mean, maybe I can say this is the high hop, low ABV cluster, but in reality, usually we have like a ton of dimensions, so that gets hard to do, but these are clusters. And so what did I do with that is basically you told me that you liked these beers. And so all I did was I just recommended you another beer with a probability close to like the other beers that you liked. So if you said that you liked all of these beers, let me make this. I guess this is fine. If you said that you liked all of these beers, maybe like 60% of the time, I would recommend you a beer from cluster 1. So this would be called C1. And maybe 20% of the time, I'd recommend you a beer from cluster 2. And 20% of the time, I'd recommend you a beer from cluster 3. So that was just a approach. There's probably a bunch of different ways you could do that, but maybe another one would be give you the next closest beer here, but the reason I did the clustering approach is because I actually think I had like a randomness factor in there where like 10% of the time or something would just give you a completely random beer just to see if you extend your palette. I don't know if Amazon does that or not, but that was some time ago. Does that help with so that found a pattern. The pattern was these circles.
Gotcha.
Yeah, so that was the hidden.
That was the hidden pattern.
Thank you.
Let's go back to, there we go. Good question. Oops. Apparently that was zoomable picture. And then again, we won't touch on this, but there is something called reinforcement learning. So if you're really into games, sorry, this is a bit of a tangent, but you guys are used to me by now. You know I do this. OpenAI, no, OpenGym. Premier Gyms. I feel like I have the name wrong. Oh, they renamed it. It's called Gymnasium. They went through some rebranding. There. Okay, it took me a long time. Sorry. Anyways, this is really cool. Or maybe I just think it's cool because I'm really nerdy. But there's this, you can, basically there's a bunch of games. This is a package called Gymnasium, and it's for reinforcement learning. We won't get to it in this class, but you can train little agents to play certain games. And what's nice about this is they've already built all of the code for the framework for this, so you don't have to do it yourself. But like they have a bunch of Atari games, so you could, if you're really dorky and had no life, you could get together with your friends and you could create, I think they have Pong in here somewhere. I swear there is. Oh, there it is. You can create a Pong game, and you can compete against your friends. You can say who can make the better Pong agent, who has the better strategy that they're going to develop for how to play the game Pong. Then you can compete against each other. It's kind of, all right. Sorry for that tangent. I'll keep that up. I'll drop that link after. So anyways, there is something slightly different. There is reinforcement learning is another one of those domains. Okay. I would be remiss if I didn't mention the most popular and quoted quote in all of machine learning and data science. You'll probably hear this about 5 billion times. So I'm gonna pull a cliche and say this. But all models are wrong, but some are useful. So we're gonna talk about what, I'm trying to decide if I want to do the break now. Let's do a break now. And then we're going to talk about what a function is, and we're going to talk about k-nearest neighbors. So let's take a 10-minute break here. We'll be back at 7:13. All right, and back to our regular scheduled programming here. So George E.P. Box made this really famous statement that all models are wrong, but some are useful. So when we talk about functions, that's what we're doing in machine learning. We are training a machine, but we're training a machine to create a function. And this function is a model of the world in some ways. And it's inherently a grossly oversimplified function because we're never going to have all of the information that we are going to need in order to discretely, accurately predict that. We're not going to be able to predict the role of randomness, for example, and what it would play in our model. So we expect that the model is going to be wrong. Your goal should never be to get 100% performance on your model. For example, if you're doing that, you probably are doing something wrong in your logic or leaking some information. You should really question. You should have a lot of scrutiny and curiosity as to why that's the result. But some models are really useful, and we can use them to make business decisions with confidence, but they're definitely not something that work 100% of the time. So let's talk a little more about functions here. All right, so if we have what is a function? Let's see if I can zoom in a little on this. Okay, so so we have input x that comes in, and our function we will represent as f of x, meaning f given input x, and then our output we will represent as y. And again, we're trying to model something about the world. Maybe we're trying to predict the price of a home. Given a new home is coming to the market, and a bunch of information about it, information meaning the number of bedrooms, what is the square footage, how many bathrooms are there. Given that information, can we predict the price that the house will sell for, given other houses that have sold for other prices? There are some rules with these functions. It's a mapping between two sets. So we have, set X. These are different observations. Sometimes they're called observations and are different outcomes or targets or labels. And for each input item, for each X, there is only one corresponding output. You can have two X's here, like X3 and X1, go to a single Y. So we can have two different houses that are both sell for the same amount of money. That is acceptable. What we cannot have is one house that goes to two Ys, that sells for two different amounts of money. That is not the type of problem that we are modeling. So there is only one Y value that we are trying to predict. So some function examples. You want to make a function that models adding 6 given a number, or make a function that gets prime numbers given a number. These are really basic kind of computer science functions, but we can transform these into more probabilistic functions, predicting a probability. What is the probability that it is a cat given an image? So image is the X set that we're putting into our function. Whether or not it's a cat, yes or no, is the Y, 1 or 0, the output that we're getting from that, and the function f of x is cat. Height from shoe size, we'll talk about this. So given, can we predict the height of an individual given the x variable of their shoe size? So what is the height, the discrete value that we would predict? And our function is height from shoe size of shoe size. All right, I won't beat that to death. All right, so this is the one we're going to talk about, height from shoe size given shoe size. So how would we write this function? So let's look at some data here. we have all these different shoe sizes that range from 6 to 16, and we have these different heights. So this is our X, our shoe size X, feature 1 that we're going to put into our model. And then this is Y, our Y that we're trying to predict. Given we don't know somebody else's height, a new person in the data set, if I gave you my shoe size, could you predict your height? Or I'm sorry, could you predict my height? Could you give me a discrete value that you think that my height would be? Or more a precise value is probably a better way to say that. A precise value that you think my height would be. And naturally, you look at this data and you think, well, yeah, I think there's kind of like a line that goes through this that could work. Oh, sorry, I already said this. Our input, so input X, so we're going to feed our data, our new person, me, maybe my shoe size to this function, and it's going to tell us what it predicts would be the output. Oh no, I thought there was more. Anyways, we'll get to this. So that's what we're going to do with linear regression. Basically, we're going to find the line that fits this data, the best fit line. You can think of this, in this case, we only have one dimension. And so you could think of this actually as y equals mx plus b. We're going to find the y equals mx plus b, the best fit line. Okay, let's pop back to, I think we're good with functions now. So we're going to get into our actual algorithms here. Our first algorithm is something called k-nearest neighbors. And this is a supervised learning algorithm, meaning we have labels for our data set. So not unsupervised, we're not necessarily clustering. We have labels for our data set. And in this case, we're given this image of a cat, and we're saying find the k closest matches labels in the data set. So k-nearest neighbors is a really simple algorithm to start with. All you do is you plot your data on some type of grid, like I have here. I was looking for this eraser. I will switch this computer view right here in a second.
So would that one be more useful for like the example that I gave?
Oh yeah, what was your example again?
If we had animals,
Yes.
and then I put in a tree, it wouldn't suggest a tree because it's not a close match.
If you had, yeah, let's do your example, animals and trees. And let me switch to the view here. This one. Okay. So let's do, we had a bunch of animal pictures, right? Oh man, I'm not going to try to draw animal pictures. I'm going to call them A1, A2, A3, and all we have are animal pictures, and they're labeled animals, right?
Sure, yeah.
Okay, so that says animal. I'm just writing it fast. So we have these animal pictures, and you have a new picture coming in, and it's a picture of a tree.
Yes.
And your query is, what is this? Or maybe your query is this an animal, yes or no? And let me take just a second to explain the difference between those two questions, because those are two different questions. If you're saying, what is this? You're asking, give me a label. Either tell me it's an animal, or tell me it's a tree, or tell me it's a fungi, or I guess maybe we should make this plant to make the kingdoms line up more appropriately. There we go. What else is there? Animal, fungi, plant. Did I get all the kingdoms? So if you're asking, is this a tree? Then you're just asking, it's either yes or it's no. Which, by the way, when we only have two labels, computer scientists have this really terrible habit. I guess it's useful, but they just change these into ones and zeros. We can't do that if we have three. We'll get to explaining why that maybe makes less sense. Or I'll just explain now. Why not explain now? We'll go on a tangent here, so I apologize. So why don't we just make these 1, 2, 3, right? Why don't we just say 1, 2, 3 instead of having these labels? Well, if we labeled them 1 and 2 and 3, basically to the model, as we will find out, we're telling the model, because it's all math under the hood and adding and multiplying numbers, we're telling the model plant is worth twice as much as an animal, and fungi is worth 3 times as much as an animal. And, so it's building those relationships between them, and that maybe doesn't make sense for our problem. So we don't typically go 1, 2, 3 with these, but you'll notice basically if we're asking 1 or 0, this is going to be a problem called binary classification. This is what we'll use logistic regression for if we're doing binary classification. You don't need to know that, we'll learn that next week. But this is what would be also a classification problem, but it's not binary. We don't have just 2 classes. Anyways, okay, so thanks for bearing with me, guys. Okay, back to your original question. Query, what is this? Let's just do that one. What is this? Is this a tree? And so in K nearest neighbors, it's going to look at different attributes about this thing. And actually in image processing, it's really interesting. What it does is if this was a black and white image and say I colored in the center here, what are our X features for an image? It's actually all the pixels of an image. So if I broke this down into a grid, and this would be like 1, 2, 3, 4, 5, 10, 15, 20, 25. So now we have a 25 pixel image. Each pixel is an input to our model. This is such a tangent. I'm so sorry. I'm getting somewhere. There we go. Okay, so if we look at this pixel here, the top part of the tree, it maybe looks like this. And so now we have to assign a numeric value to that. Maybe that's 0.5. It's 0.5 illuminated. So on a scale of 0, where 1 is this, fully illuminated, that's like this square here. We can think of this as 1. And this square here is not illuminated at all. So we can think of that as 0, and this one's 0.5. Basically, it takes all of these in as the features. So the vector would look something like 0, 0.5, 0.7, 0.3, 0, 0.2, etc. And so that is what all of these, that's what that image translates to. And so it's going to take all of that information, and it's going to take all of these numbers, these pieces of data, and it's going to say, who is closest to me? What are okay, so now we're getting to the point, what the heck is KNN? This is a really complex example. I'm so sorry. I have simpler examples. So when we get to KNN, it'll say, who is most similar to me? So maybe there's an answer that's like 0, 0.4, 0.6, 0.3, 0, 0.2. Well, if we subtract these two numbers, if the distance from 4 to 5, 0.1, the distance from 6 to 7, 0.1, these are all 0, and we take the sum of that, it's going to be pretty small. Maybe it's like 0.2, right? So these two things are really close. So we would look for in KNN, it's called K nearest neighbors. The K is the feature, the parameter. We're going to have parameters today. The parameter that you're going to choose, and it's just how many neighbors do you want to look at? Do you want to look at 2 neighbors? Do you want to look at 5 neighbors? Do you want to look at 10 neighbors? And then whatever the labels are on those neighbors, those are your votes, and you take the highest majority vote. So if all we have are animals in our data set, and it said, what is this? And it gave this, it would actually only be able to say it's an animal. So I finally got to answer your question, because all we have are animals. So all of its neighbors are going to be animals.
Okay.
because it's the only other thing in there. So we would actually need other examples.
And I was gonna say, unless we introduce more trees.
Exactly. So you actually pointed out a really, really good like foundational problem with machine learning models is it only learns based on historic data. So to your point, you have a tree, you know it's a tree, but there's no other trees in our data set. So our model is something we call biased. And this is a real problem. If you look at some companies train machine learning models to go through their resumes and algorithms for them. And did you know that if you gave it 2 resumes and they look exactly the same, and the only thing you did was you changed the name to a man's name instead of a woman's name, it would have a much higher probability of acceptance of being promoted. And so that's called bias in an algorithm, and that's due to our training data, right? So there's techniques that we need to employ as people who train these models to trick the model or teach it how not to make decisions in that way. So we'll get to that. Sorry, that was such a tangent. Thank you guys. Whew, apologize.
That was helpful.
Okay, I hope so. I promise we're gonna go through a much more simplified example.
It's like grading was simpler.
You piqued my curiosity with everything in our training set is trees or is animals. Okay, so let me see if I switch back here. So when we're talking about, you guys see that okay? Yeah, you see that okay. So when we're talking about k-nearest neighbors and we're given the query on this item, there are some features about these pictures, either the pixels in that insanely complex example I gave, or maybe some basic features like, does the picture contain the color brown? Yes or no? So there's just some information we have about these pictures, and whatever that information is, those X variables, we're going to find the nearest neighbors to this. So in this case, all we're saying is for our target data set, we're just returning the most frequent label. So if a bunch of different people labeled this picture here, whatever the most frequent label for that is, that's what we're saying is our label for that. So if k equals 3, here are the 3 closest neighbors to this picture. For whatever reason, we don't have a label for this picture. We see it's a cat, but the model that has no label for this picture. And when we give it to the model, these are the ones that it's been trained on. So it's been told, this is a cat, this is a cat, this is a cat. And so we look at its closest neighbors, again, based on those X features. I'll get to another example about that. And so in this case, if we said k equals 3, meaning look at your 3 closest neighbors, then it picks these cats. It chooses cat. It says, hey, I've had 3 votes for cat. That's the majority class vote. I believe this is a cat. If we said pick broaden your set of neighbors here, and we said maybe we have like one that's a cat, one that's a buffalo, one that's a deer, one that's a lion. So there's some dissenting opinions here. But still, we have 2 votes for cat. And so cat wins. So this is a really, really good algorithm to get started with. And I would recommend that you guys apply this to your iris data set. So given your X variables about your iris flower, can we find which are the closest neighbors for that? So again, that'll be part of your homework for this upcoming week. A little more about this. This is maybe perhaps a slightly better visualization, and there's a little more words, a little more description in here, so you guys can check this out. But this is the visualization that I liked. So when we talk about your X features, So we've already decided this is category A and this is category B, but now we have a new data point here. And we want to know which category does it belong to. Does it belong to category A or does it belong to category B? And the way that that is actually determined is we look at the nearest neighbors, in this case, 5. We use distance, and there's a bunch of different distance metrics. There's different ways you can alter these algorithms. Their core logic principles, the steps that they take are the same, but there's slight tweaks you can do, which are typically parameters. So you can use Euclidean distance, if you guys remember that from middle school, kind of elementary school, or there's a bunch of different distances you can use. But basically this measures, and we can see, oh, there's 3 green ones and there's 2 blue ones. So we've decided that this is a green one. So that is actually, there's no picture showing it's a green one. But this will walk you through the KNN algorithm here. One question might be, how do you choose the number of K? How do I know if 1 neighbor or 2 neighbors or 6 neighbors or 20 neighbors? How do I know the right K value to choose? And there's a graph which I'm hoping will pop up if I click on one of these links. It's called an elbow curve, which I think is a clever and funny name. And maybe I should just search that. And it can help you choose the optimal K for your method. If I can't find it on this link, I'll send it after. This is kind of when you don't, it's not as pretty. I'll try to find one that's a little more of a classical example that's incredibly extreme. But basically, you plot your error rate for all your different values of K. So on whatever this data set is, this individual tried 0, 2 values of K, 5 values of K, 10, 15 neighbors, 20 neighbors, tried looking at 30 neighbors, 35, 40, and you could see this error rate going up and down and up and down. They call this an elbow curve because it tends to sort of look like this L. It looks like an elbow. And so your value of K, you usually try to select along this elbow area. Once you get up to these higher level of neighbor selections, you start to see this performance, this error rate kind of platform out a little bit. And so you want to select where you don't want to select way up here. It's not very good. You're not doing a very good job. You have a really high error rate at the top here. So you want to select a little closer in here. So basically you train a bunch of different models on a bunch of different values of K. And then you look at your error rate versus your K values. And then you try to choose sort of in this elbow area. Okay, I will send that out. Let's see what I have on KNN. This is a good point made here that I hadn't really thought about before, but no training is needed for KNN. Right? We don't have to train a really big machine learning model for this. We're just looking at the neighbors that are next to where that point lies in space and seeing what those labels are. So from that perspective, it's a pretty fast algorithm. And it generally gets a lot better with more data. It's simple and it's fast. And the only parameter is K. We talked about this, the number of neighbors. If you want to add weights or choose your similarity metric. So we talked about that. What's your distance metric or your similarity metric that you're choosing to decide 2 things are similar? Doesn't necessarily have to be distance. So you can use a bunch of different distances. We won't go through these, but Manhattan distance, this is coordinate-wise distance. So basically we're or doing what I did on the board, I just took two values, I subtracted them from each other, and then I took the sum of those, right? So I took your vector 1 and vector 2, and I lined them up next to each other, and I said for x1, for the first feature, what's the difference between the two? For the second feature, what's the difference between the two? For the third feature, what's the difference between the two? And then we took the sum of all of those. So there's different metrics or distance metrics or similarity metrics that you can use, but it's up to you in your problem space. Okay. Any questions on KNN? That's our first machine learning algorithm. Okay. I'll show you guys the package for that too, actually. I should really do an introduction on sklearn. You know what? I'll do that for the recorded session. I just realized you're going to need that package to do all this. We're not doing too bad. Just 10 seconds on sklearn here, and I'll maybe go more in depth. I know you guys have already touched on it with the iris data set, but sklearn is going to be your friend in all things machine learning and data science. It stands head above the rest as the best machine learning toolkit. I'm going to say of any programming language that exists today. It's incredibly well developed, very well thought out. It's open source, so a ton of people contribute and add to it. You might hear it called scikit-learn or sklearn, same thing. So they have different types of things here. So they've got classification, regression, clustering. You guys know what all those are now. We've talked about that. They've got pre-processing, which we'll get to, model selection, which we'll get to, dimensionality reduction, which we will probably not get to. But if we go to regression, which is what we are talking about, regression, remember, that is when we're trying to predict a scalar output. So remember that is, oh, I'm sorry, we were talking about KNN. That is going to be classification. I apologize. Sorry, I'm jumping ahead of myself here. So classification, remember, we're trying to apply a label to something. We're trying to say it is or isn't this, or we're trying to say what type it is. So think the iris data set that you guys have been working with. So they're going to have a bunch of different models in here. So we're going to have different types of models. So we're going to have linear models, and we're not going to get to QDA or a lot of these things, but you can just see how many different models there are in here. And look here, now we have nearest neighbors. So there's a ton of different nearest neighbors. Let's see, we're doing nearest neighbors classification. You know what, I'm just going to Google it. So they have such there we are. So this is going to be the quote unquote algorithm. The nice thing is you guys know all the steps, but I'm not going to make you code it by hand. You're just going to use like standard packages out there. So this is the sklearn.neighbors.kneighbors classifier. And the way sklearn works is it'll have your import here. So this is what you need to do to import it. And typically if you scroll down, they'll have an example at the bottom. I find this really useful. You can copy, this code here. Don't forget, don't copy these carets here. That's just them showing you that's what the input is. And if there's no carets, don't copy that either. That's just them showing you that's what the output is when you run these pieces of code here. So this is how you would import it from sklearn.neighbors, import kneighbors classifier. And they're making their model, they're calling their model nay is equal to kneighbors classifier. And remember, we said only one parameter you have to pass to it, and that's just n neighbors. And in this case, they chose 3. I would recommend for iris dataset, just choose an arbitrary number for now for your classifier. It doesn't really matter for the homework assignment, we will talk about cross-validation, and we're going to build on this slowly. So for now, don't do train test split, don't do cross-validation, don't try to select the right K unless you're really enjoying it and really want to do that. But for now, just create a classifier here. Just take this code, this import, and create this nay, and then run nay.fit and pass in your X data and your Y data. And that's all you need to do for that one on your, and then if you want, you can predict too, or you can check the accuracy or whatever, but you don't need to do any of that. We'll talk about, just make your model for now. We'll talk about evaluation later. So sklearn neighbors, so this talks about the different parameters. So while there is only one required parameter, which is number of neighbors, and it isn't even required actually, it defaults to 5. So you don't even have to pass number of neighbors. You can just run this K neighbors classifier, open parenthesis, close parenthesis. You don't have to put anything in between there. But these are the other parameters. So this is how you would read this. You would say, these are the types of parameters you can pass it. You can pass it n neighbors. You can pass it weights. You can pass it algorithm, leaf size, all these different things. And then this is the default value. So the default value is 5. The default value is uniform. The default value is 30. That means if you don't explicitly pass a parameter, it's going to default set the leaf size to 30, which is probably fine. So these are a little more deep explanation of each of their parameters. This is the parameter name. And then on the other side of the colon will be like the values that it's expecting you to pass on that. We'll get more familiar with this as we go. Really don't pay much attention to any of these parameters except n neighbors. If you're interested, you can just play around with different neighbor values and see how it changes your model performance if you're curious about that. Okay, I'll send something out that's maybe an example of working with k-nearest neighbors on a different data set. So I know that's a lot there. All right. So that's k-nearest neighbors. Okay, the heart of our discussion here, the way that we're going to spend our last hour here is on linear regression. This is such a foundational and a really fundamental algorithm in machine learning, no matter what class you take. Some classes, maybe they'll teach you naive Bayes or I'm teaching K and showed you guys K and N, but somebody else may not show that. No matter what class, they will always start with linear regression because it's kind of where it started. There's so many reasons why. One, it's just a really good foundational piece if we look back and we want to know where did machine learning come from. It's really easy, or it's really good to look back at linear regression. Also, it's a nice way to view and model the world because it's easy to wrap our heads around in these 2 dimensions. We can start in 2 dimensions with linear regression, which is really nice, just an X and a Y. And then we can start to build a foundational understanding. But also, as we get into logistic regression and other techniques along that line, that's what's used in neural networks, in building the nodes and decision boundaries for neural networks. So it really is foundational. So we want to, it's foundational, but also don't be overwhelmed by the term linear regression. All we really want to do is just find the best line that fits a linear function. I'm sure you guys have done this a million times. We have a bunch of data and we just want to run best fit line. I think there's a function in Excel that does this. And so y equals f of x. So given all this data, how do we know that this is the best line? Like visually, we can look at that and it kind of looks right. But what if the line was up here? Or what if the line was going this way? Mathematically, what is a number that we can use to say this line is this much better than this other line that I just made up? Like, how do we know that? And how do we plot this exact line? So we're going to use our, oh, I thought that was going to be the next slide. Sorry, we will get to that. So this is the formula for linear regression, not logistic regression. This is the formula for linear regression. So our predicted value, remember, this is a hat, by the way, this little up caret. I don't know what the appropriate term for that is, but when we say y hat, maybe somebody on the phone knows what the right term for this accent, maybe, perhaps. This accent on the y, that's called y hat, and that means we talked about functions being models of the world, and out there in the world, theoretically, there exists a function that is exactly correct, but we will never be able to get to that function, and so we use y hat as our oversimplification for as close as we can possibly get to that function, or y hat represents our function that we're making, but isn't the actual function y. And so that's what that is. But usually we'll just simplify and call it y, so we'll get there eventually. But y hat, so our output equals beta sub 0 or sub naught plus the sum from j for all p for x sub j beta hat sub j. Oh my goodness, what is all this? It just looks like a mess, right? So it's really simple. This is actually just y equals mx plus b. They just decided they wanted to put it in some complex notation. Basically, the second piece here is just saying for all other values, sum them up. So let me see if I can even. So m, remember m is our actually this algorithm starts with b, m1x, sorry. Let me type this out and then there we go. So basically this really is just y equals mx plus b, but in this case we have lots and lots of m's. So m might be our shoe size and we want to predict height, but maybe we also have the gender that somebody is, and that, men are taller than women, so that maybe that's a feature that we use. So in this formula, we have y equals b, mx, in our mx plus b formula, that's what beta sub naught is. All it means is our intercept, if you guys remember our intercept term, and so beta is going to be right here. That's our intercept. Remember, that's where we start. So if beta was 10, our line would be up here, but directly parallel. Or if beta was 0, our line would be down here. So that's what the beta is. Beta kind of represents if all of our other features were 0. So if somebody had a height, and we're trying to predict, given shoe size, predict height. So if somebody had a shoe size of 0, what would their height be? And so if they had no shoe size, what would their height be? And that would be represented by this beta sub naught. In the real world, you're like, what does like a shoe size of 0 mean? Well, maybe that's a baby. Like maybe a baby has a shoe size of 0. What would the height of a baby be? And so sometimes you can interpret it to real world things and sometimes it makes no sense at all. So just be aware of that. But the reason why are the other ones 0? It's because M1, our shoe size, if it's 0, M1 times X is 0. So then you would end up with, if all of our features were 0, you would end up with beta, maybe that's like 20 inches. I don't know, it's that baby's height when they're born, plus M1 being our shoe size. Our shoe size is 0 times, let's just make up a value here, 2. So in our model, we're saying that for every 1 shoe size somebody grows, they go up in, sorry, I'm going to put these in weird metrics here, just bear with me. They go up in 2 feet in height, for example. But if somebody has a shoe size of 0, well, 0 times 2 is 0. So now it's just y equals 20. So that is what this beta sub naught is. It's our intercept. You can think of it as our default value given all other features input into our model have a value of 0. So we have no information. So if you're building a house, the number of bedrooms, none. The square footage, none. All of that information is all zeros. Then what is the price of your house? Okay. So the couple of terminology points here. We typically call these beta hats, these weird looking bees, we call them coefficients. That's a really common term. You might also hear them called features. Generally, it depends on who you're talking to. If you're talking to a machine learning person, they'll call them features or feature weights. If you're talking to a statistician, they're probably going to call them coefficients. What are the coefficients of your linear regression model? And that just means what are those values, those weights? We'll get to that. That's fine. We can skip that. That's some matrix stuff. So this is nothing fancy here. Sometimes you'll see, just want to highlight in notation, sometimes you'll see X as you're reading stuff represented as a matrix, where this is 1, 1, meaning it's the first observation and the first row of data for that first observation. So if it's Emily, it's Emily's observation in the first row, Emily's observation in the nth row, or somebody else's observation in the first column, somebody else's observation so M person, nth column, M observation, nth column. So that's all that is saying. Sometimes they like to generalize things to many other applications. So one thing you'll see a lot is the residual sum of squares. And I'm trying to decide where I want to start here. Let's actually jump to okay. So for simple linear regression, how do we know the line is a good fit? Well, really what we're going to do, there we go, is we're going to plot a line somewhere, and we're going to look at all these other points, and we're going to calculate what is the distance between this red line and this blue dot, and this red line and this blue dot, and this red line and this blue dot, and we're going to do that for all of the dots. How far away are they from our red line? And the reason we're asking that question is, remember, this goes back to the model that we had talked about, where you had the X's and the Y's, and for every X, multiple X's can map to one Y, but they can only map to one Y. So that means that if you have a shoe size of 20, I know that makes no sense, but we're going with the shoe size thing. If you have a shoe size of 20, then it maps, the model will predict, we draw a straight line up from 20, it predicts this at the red line. So what is that, like 8 or something? So it will predict 8. And so it predicts 8 for all, no matter what, for all of the values that have a shoe size of 20. But you can see that there is some disparity here, right? There are people who have variety, probably because we have other features that we haven't considered about these individuals. Remember I said that a model is a representation. It may be useful, but it's not correct. And so this is one example of that. And so this running the distance to the line to what the model would predict at that point and what the actual prediction was. So the red line is what the model would predict, and then the blue dot is the actual ground truth, the real representation. So basically, we're going to calculate the distance from all these blue dots to this red line. For all the dots, we're going to sum all of that up, and then we're going to square it. And the reason we're going to square it is because some of these will be negative, right? This is, if it's below the line, it's going to be a negative value. If it's above the line, it's going to be a positive value. And if we didn't square it, those negative values and those positive values would cancel each other out. So we have to square the value so that the negative values become a positive. When you square a negative number, it becomes a positive. Okay, there was no good picture for that. So, oh wait, maybe I jumped ahead of myself here. Yes, I jumped over the slide. So this is what we are trying to do. Here's a better representation than me just using my mouse. So here's a line here, meaning this is our function. This is the line, the y equals mx plus b. This is our formula. And we're going to calculate the distance here in yellow of every single dot to the line. So maybe this is 5. Maybe this is -2. Maybe this is 4. We're going to square those, and then we're going to add them together. When we are given x, when we're given a new point, this is a new point, we want to know what y is. So then we just follow up to the line and then come over here, and then whatever that value for y is would be the output there. So each point and the difference between the predicted point and the actual observation is something called the residual. You'll actually, not residue, but residual is what you'll probably hear. And so this yellow thing here is the residual. It's the difference between our prediction. Our prediction is always this dot on the black line, and the actual point, which is the residual. Okay, does this make sense? Okay. This is the most useful graphic, I think, so I hope that's helpful. We're gonna look at the formulas for that. So for simple linear regression, we're going to use the sum squared error, which is the SSE, you'll probably see it called that, which it means we take all of our predicted values minus all of our actuals, and we square them. You'll see this sometimes called residual squared or R squared. So if you've ever heard R squared, what's your R squared value? People ask that a lot. You are reporting this exactly here. The sum of squared errors, R squared, residuals, all the same thing. There's another metric called mean squared error, MSE, which is just a slight derivation on this. All you do is you take the mean. So all similar metrics. But basically, it's predicted versus actual for every single point in the data set. And while we're doing this for linear regression, you will see this pattern over and over and over again with other data, with other metrics of performance. It's predicted. What is your predicted value minus what is your actual value? What is your real value in your data set? So you'll see that a lot. So in this case, if we predicted a house was $150,000, but actually it was $200,000 because inflation has been crazy, then we would take $150,000 minus $200,000, which note is negative $50,000. But again, we don't want the negative. We just want the actual difference. And so we take that number and we square it. I don't know that off the top of my head, but that would be your residual for that example. You do that across all of the data points in your training set. So, and you don't need to do this by hand, by the way. We'll just plug it into a metric, but this is how it works. It's very helpful to know how these algorithms work under the hood, because if you're applying for a data science job, the most common question in the industry is going to be, pick a data science algorithm, any algorithm of your choice, and walk me through the steps. So you can pick k-nearest neighbors, you can pick linear regression, you can pick logistic regression, or k-means. You can choose any of those. My personal favorite's random forest, so maybe we'll get to that, or we will get to that eventually, but not today. So you might ask, how do we learn these very, very powerful things called coefficients or parameters, as they're sometimes called? These beta sub 0, beta sub 1s. how do we learn what these are? How do people say, like statistically, oh, a house, if you add a bedroom, it's going to add $10,000 in value to your house. Well, we're going to build a data set that will actually be able to do that for us. And I might have skipped that. So in this, so how do we do that? I did skip that, sorry. We minimize an objective function. So we have an objective that we are trying to do. And in this case, the objective function is what we're trying to accomplish. In this case, the objective function is that SSE, so that sum of squared errors. We're trying to minimize the difference between the predicted and the actual outputs. So your algorithm will go through a bunch of different iterations, and it'll say, oh, the difference between the predicted and the actual is really high. So I need to change this number a little bit and get that predicted and actual to be a little closer together. Because remember, we have a training set, so we have labels for these. I will not go over, I think there's a ton of value in going over these formulas, but maybe I'll send a video afterwards that goes through these a little more in depth. Let's see. So we talked about this. It's the difference between the predicted and the actual. We don't want them to cancel each other out. This is a good visual because here's one more useful visual here. We don't want them to cancel each other out. So we could either use absolute value. So you don't have to square it. You could use absolute value instead. That would be another approach. And that is another metric. There's a bunch of different metrics you can use. But in this simple example, we have these 3 points. And we want to find a line that is the best fit between these 3 points. So we could make a line that goes between these first 2 points. And this house is way down here. So it's our line. We're just doing y equals mx plus b. So our line has to be straight because all we've got is b, an intercept, and m, a slope. We don't have more dimensions than that. And so you can see that the difference here is 7. So we're going to have an error of either 7 or 49 if you use the squared value there. Or we could make another line. And maybe this line goes through these 2 points. And this one has a value of 5 because the difference between this point here and our new line is 5. That's our error, or that's our residual. And if we square it, our r squared, it's 25. 5 times 5 is 25. So that's our r squared. So we can now quantitatively say that the red line is better than the orange line. This is a better model of these 3 data points than this one. But is there an even better model? Well, what if we took a line? What if we took a line, and it's horribly bright, so really hard to see, I apologize, and we went straight through the middle of these 2 points? What if we, didn't go through either of these 2 points? Instead, we started at this point and we went through the middle. We cut it in half. Well, the distance to this one is 3, and the distance to this one is also 3. Neither of them are directly on the line. So the actual here is plus 3 for whatever that value is. And this is the predicted value. This is the predicted value. And this is the actual value. And they have a difference of 3 here. So 3 plus 3 is 6. And then you could do 6 squared if you want to do an r squared for 36. So r6 is actually higher than 5. So this line is actually a worse model than this line. And it's really hard to tell, right? We can't just visually look at it and say, oh, definitely this red line on the bottom is better. So this helps us quantitatively assess that the red line on the bottom is better than these other two lines. Now, this is obviously a very simple example. We've only got 3 points, but generally this is how this works. And this will generalize to your larger data set as well. So if we had an input of, for this yellow line, if we had an input of 2, this is what it would predict. If we had an input of 3, this is what it would predict. I think, how much more do we have in here? Okay, just a couple more slides. Let me see if any of these have value here, and then we'll take a break. This is a good point. So we can always apply a linear model, but a linear model will not model all relationships well. So we've been talking about data that looks like this and applying a linear model to it. And that makes sense, right? There seems to be a linear relationship in this data. There seems to be a relationship between X and Y. When X increases, Y increases in this data set. That is not the case here. When X increases, well, it does a different little function here. So a linear model probably doesn't fit this data well. It's hard to turn this line different ways, to twist it around in space and try to get it to fit this model. You might have outliers in your data that can make it really hard to model. This line, as you imagine, might actually fit really well going through these points. But you can see that this one outlier pulled that entire line up because the algorithm is trying to minimize the R squared. Remember, we're trying to minimize the distance, not just from one point, but across all the points to the line. And so if you dropped this from the data set, you would dramatically see this line basically shift down and follow these much better. You get a much better fit on your model. So outliers can have a big impact on these linear models. And then this data is quite hard to model in this way as well. Maybe not the right type of model to choose for this. So regression models, linear models, really good, not applicable or doesn't make sense for all problems. And it may be something you may just have to research and kind of figure out along the way. So this is the formula for the R squared value, or here's a formula for the R squared that we've been talking about. It's just a different way of looking at it, where Y sub I is your predictions, Y hat is what Y sub I is your actual values, your labels, your true values, your ground truth, and Y hat is your prediction that you were trying to make. Oh, that's just showing the slide one. Okay, that's assessing good fit. We'll get to that later. I think we're good on linear regression. Let's take a 10-minute break. Let's come back at 8:22, and then maybe we'll spend the rest of the time getting started with linear regression. We didn't get to some of the clustering stuff, so we'll come back to that probably next time. All right, 8:22. Okay. For the final kind of portion for class today, I want to get to any questions that you guys have first. And then after that, I just want to walk through this this data set here, maybe applying, walking through an example of applying a regression algorithm to a data set. So we have this another toy data set. sklearn's great. They have a bunch of toy data sets in here, so we don't have to worry about importing reading from a CSV, which we'll get there. So we'll talk about that. And then if there's time, I'm going to talk about reading from a CSV, and I'm going to touch very lightly on feature engineering, and then I'll add that into my next lecture if we don't have time. So that's kind of the plan for the rest of our time. First of all, do you guys have questions?
No.
All right. If you do, just interrupt me. So I promised we would build a model every day, so we're going to deliver on that promise here. We're going to look at this diabetes data set, which has a bunch of different variables. So we have age, sex, body mass index, BMI, average blood pressure. So you can see all those down here. Here's our attributes. When we say X, we've been talking about X in abstract, big X, big capital X. These are our X values. So now we're talking about real tangible things here. So age in years is one of our X values. So when we say X sub 1, that's age in years. X sub 2, that is sex. X sub 3, that's our BMI. X sub 4, that's blood pressure average blood pressure. So you get the idea here. So these are our features. Given somebody else, a new person in our data set, you're going to give me all of X, and then the model that we train will predict Y. Well, what is Y? Our target variable, otherwise known as column 11, it's a quantitative measure of their diabetes progression 1 year after baseline. So it's some measure of diabetes progression. And I think we should note that all of these patients, each row, each record in this data set is a patient. And it's a patient with diabetes, and there are 442 of them. And what the variable is their quantitative measure of progression 1 year after baseline. So given a new patient, we predict what their quantitative measure of disease progression would be 1 year after baseline. Obviously, this is going to look different for every single individual. How do you get such personalized predictions? Remember, we talked about a model. It's a oversimplification of the world. We're trying to map X features to one Y output. And you can imagine, maybe we tacked on even more information. Maybe we knew every detail of their childhood growing up, or maybe we knew all of their interactions with their family member. Maybe we had a data set that was 70 terabytes large for each and every individual. Well, maybe then we could get a really accurate prediction. But first, we're just going to simplify. So we're going to create a very simplified model with just these sets. These are feature variables. You'll see that a lot. These are what it's referring to as attribute information here. Okay, so let's build a model. I put all of my imports here at the top. So we're importing NumPy as NP. You guys are used to doing that. That's kind of our nomenclature here. And then we're importing pandas as PD. We're importing matplotlib as .pyplot as plot, PLT as PLT. Seaborn, this is another visualization library we'll talk about later. You don't need to know anything about that, but we're going to import sklearn.linear model. We're going to import linear regression. And how did we find that, first of all? So let's say I want to build a new model, and I decided it's linear regression. You can search sklearn and then the model type you're looking for. So in this case, linear regression, or maybe I want to define KNN, or maybe I want to define k-means clustering, which we didn't get to talk about, or maybe I want to find random forest. So when you're looking for an algorithm, it's usually just going to be the first tab down after this. So let's look, let's get back to logistic regression, or I'm sorry, linear regression. I don't know why I keep mixing those up today. So how did we know how to import that? We just click on that first link. It'll take you to this here. This looks like a lot like the KNN. You'll notice their format will be the same. Here is the simplified kind of model. It exists in the sklearn package. Within the sklearn package, it exists in the linear model folder, and it is the object linear regression. And we have all these parameters that we can pass to it. We're not going to change any parameters. We're just going to build a basic model. We're not going to change anything about it. So this is how you would import it. They have this nice little example code in this example section at the bottom of most of their documentation. So you can just scroll down from sklearn.linear model, import linear regression. And they even give you an example of how it works. X, so they're creating some X data here, some Y data here. And they're saying create a new object called reg. And that is going to be equal to, I'm going to assign that the value of linear regression, which we got up here from the import statement. We said import linear regression, so that's where that comes from. Linear regression, pass it no parameters, don't change anything about it. I just want the base model. And then called .fit, big X, little y. So your big X is here, that's your X features, your X training data, and then Y is your targets. When you fit a model, remember this is supervised learning. So we have labels, so we have to pass Y labels. That's how your model learns. It checks over and over again, what are the labels, and it figures out with regression. Remember we talked about R squared, so it minimizes that loss. It tries to find the line that minimizes that R squared value. If you want to see how well your model does, you can call reg.score. You can just call their score function, and you can pass it your X and your Y. We'll get to model methodology later, but for now, that's just fine. You're just scoring on the same data that you trained on. That's fine for now. Okay, so that's how you use it. Let's actually see it in action. That's kind of their example. So the nice thing, the reason I like the sklearn toy data sets is because we haven't talked about how do you read from a CSV, how do you read from like SQL Server, how do you read from Teradata, how do you connect to all these data sources. We haven't done any of that yet, so the sklearn package allows us to just load the diabetes data set without doing that. So we can load this, we set as frame, our parameter as frame is true, so it loads it as a pandas data frame. We can run this x.info if we want to understand what these different columns are: age, sex, BMI, BP, S1, 2, 3, 4, 5, 6. We didn't look at those, but those are, you can see there's descriptions for them too. So S1 is their total serum cholesterol. S2 is their low density lipoproteins. So you can check out what those are if you are curious. You can just build a little correlation matrix if you want. I just put that out there for fun, but we're going to, I'm going to run train test split. You don't have to do that with yours. We'll get to this methodology eventually, but I'm going to basically train a model just over our training model. So we're going to use that same pattern that they had in sklearn. We're going to set, I'm just calling it something different, called it REGR instead of reg, and equals linear regression. So again, didn't change any parameters. There's nothing inside of our parentheses here. And then we're going to train our model with our training data set. So we're going to call REGR, which is what we named our, you have to call the same name of our object, .fit, xtrain, ytrain. Now, one question, natural question might be, well, why couldn't I just go linear regression dot fit on our X train, Y train like this? Well, you can, but if you never save your object back, so if you don't save your linear regression object back, you can't make predictions on it later. So you need something to use to make predictions. So you can do it that way if you want to do it all in one line. I think that will be fine, but you need something to make predictions on later. So if I go reg2 dot predict x test, there we go. That, oh, because those are the predictions. Okay, sorry, I'm getting ahead of myself. Let's just get to, let's delete all this. Get back to where we were. Okay, so we have our object here, and we're creating a linear regression model, but this is just a baseline model. We haven't done anything with it yet. It isn't, it isn't anything. So let's look at what that is. It's just linear regression, but if we call predict, it's not going to work. Right, so we get an error. It says, well, your linear regression instance has not been fitted yet. Call fit with the appropriate arguments before using this estimator. So all models in sklearn are called estimators. Fitting just means training this model. So it's telling me you haven't trained this model, and I haven't trained it because I reran this. So every time I rerun this cell, I overwrite that regr variable. So it's saying you haven't trained this. It's just it's a linear regression object, but it's not fit. So we have to fit it. To fit it, remember we have to give it data. We have to give it training data and target labels. So if we look at xtrain, this is xtrain. Remember we talked about our pandas data frame, how it kind of looks like in Excel. So these are all the numbers that are associated with this. You'll notice that perhaps age looks a little nonsensical here. It's likely that age is a scaled value. Let me make sure I just didn't do something weird here. Let's look at the original data set that I loaded in. Yep, still original one was strange looking like that. Let's see if they say. They do not say here. I bet we could go to this documentation and find out. So you're being exposed here to a very important part of like the data science process, which is understanding what is the actual data that is going into your model. So I'm jumping straight to the modeling, but really you're going to want to take a step back, and because we only have a month, so I can't do the whole process, but you're going to want to take a step back and ask yourself, what is age? Why is age 0.06 here? It's very likely that it's a scaled value, which just makes our lives easier because you don't have to do a bunch of feature engineering on this. They've already done that for you. So this is xtrain. These are X features. When we say that we have a new person come in, they're going to tell us all this information about this new person that came into the hospital. And they told us, they filled out their little form, and we ran some blood tests, and we populated all this data. And now we want to predict in another year, what is their value going to be for their, I want to use the right terminology here. They said it was their quantitative measure of disease progression 1 year from baseline. I don't really know what that means. I don't know what 189 versus 68 versus 158 does. I'm not familiar with the domain. So you'd have to, you know, if you were doing a problem on this data set for somebody for your work, if you're actually assigned to this work, you would want to understand what is that actual Y value that we're trying to predict. What does it mean this 1 year? What do these numbers represent? And maybe somebody here does, but I don't know what those actually represent. So, but anyways, we can fit a model. So then you're going to call reg_r, which is your object name for your model. Remember, we haven't passed it any data yet. And we're going to call it fit. And we're going to pass it our X-train and our Y-train data. What's really nice is this is a bit of a learning curve the first time, but once you learn the syntax, it's exactly the same for every single model in sklearn. So you're going to do, no matter what model you're doing, you're going to call .fit and fit it the same way. So let's look at, we talked about KNN. In your neighbors classifier, how would you do that? Well, we import our model from our sklearn package. We make a new variable. We assign our model to that variable. In this case, we're defining a specific parameter, but you don't have to, but we're saying the number of neighbors is equal to 3. And then you call .fit, and you pass your X and your Y. And then you call .predict, and it returns predictions. In some cases, you can call .predict proba if you want a probability, not just a discrete value. But that's not regression, that's classification. So we'll get to that.
Can you go back to where it says, n or neighbors equals 3? What does a 3?
That's a great question. So in k-nearest neighbors, we can decide how many neighbors that we want to look at. You can either look at,
Whether at 3 on both ends?
it would be a distance metric in space. So imagine like a sphere, and there's a bunch of points in there, and you put a new point inside of that sphere. Who are the closest neighbors to it in any direction? So it could be up, it could be down, it could be left, it could be right. If we're just kind of in space, who would be the closest? So you'd calculate the distance to a bunch of different neighbors. And then whatever the closest one, maybe there were 2 over here, maybe there was 1 over here and 1 up here. If n was 4, then those would be 4 closest neighbors. Okay, good. Yeah, sometimes the 2D plane isn't like super helpful. Maybe think of us all as fighter pilots in the sky, and we want to know what are our closest fighter pilots. So in this case, we're saying 3 closest neighbors. You could say 20 closest neighbors, 900 closest neighbors. And then you would look at your 900 closest neighbors in whatever the highest classification was, meaning if 899 of those neighbors were labeled flower type 1, then you're probably flower type 1, because you're right next to a lot of people. You're kind of in the middle of the cluster. Okay, so we call reg.fit, we pass our training data, we pass our X data, and we pass our Y data. And so now we have a trained model. After we call this, we can call reg_r. It looks exactly the same, but I'm pretty sure there's a function that you can call like isFit to see if it's fit. I'll look that up later. But one way you could test it out is just see if we don't get this error this time. So we're going to call reg_r.predict on our test data set this time. We'll talk about methodology later, but maybe this will be your first introduction to the difference between training sets and test sets. So we trained over a training set and we're predicting on a test set here. So if we see what that looks like, so there's a bunch of values here. You can see this is basically the value for the first person in X test. So if we look at X test, I'm just going to print the first 5 rows here. But if we look at X test, so for this person with these values, this is the prediction. The prediction is 82. For this person with these values, this is the prediction. It's 106. So this will go, the way this goes is it goes down and then back up. Pretty sure. Maybe it goes across. Here, we can check. Let's see. If we slice at the first position, remember we're 0 index. So I'm going to slice the second, or I want to get the second value, which is at the first position. Let's see if we get 100 or 106. We got 100. I was wrong. All right. It goes across. Here we are. So it goes across first. So the first record, the second record, the third record, the fourth record, and then it goes back to the fifth record, the sixth record. So that is how those are all printed. So that's great. We talked a lot about R squared. How do we know our R squared value? We're gonna call this function. I'm gonna move it outside of all these statements and stuff so we can just look at it maybe a little more simply. Here we go. This is what we're doing. We're taking something called R2 score, which you're like probably asking, where did you get that? Well, if you scroll back up, sklearn has a bunch of different metrics. You can look at sklearn metrics. This one's probably fine. Yep. So it even tells you for your problem type, which is really nice. So it says if you're doing classification problem, you can use these types of metrics. If you're doing a clustering problem, you can use these types of metrics. If you're doing regression, you can use these types of metrics. So it even gives you your metrics based on your problem type. So that is sklearn.metrics, but we're just going to use this one called R squared score, R2 score, which stands for R squared. So we talked about R squared being the difference, or it's otherwise sometimes called the residuals. You'll hear that a lot. And to calculate that, what we need to pass it is y-test and the pred. So what is y-test? This is y-test. So if we look at this, we look at our pred. Remember, our pred was 82 for the first one. We look at y-test. This is the actual values. It was 104. So we would take 104 minus 82, the difference between those, and square them. So we would take 104 minus 82. I have to remember how to do squaring in Python. I think it's star. There we go. So that is the squared for one of those, the first one. And if we want to, let me comment that here. The residual for the first prediction. Let's look at the residual for the second prediction. The residual for the second prediction, and then I'm going to do the sum of squared errors for the first and second prediction, just to give you guys an idea of how that works. Okay, so let's look at the second prediction. All right, remember we called reg.predict and we passed x test and we called it on pred. And so the second prediction is 100. And let's see, it's actually 118. So we would take 100 minus 118, or I might flip that around, 118 minus 100. Actual minus predicted. And then we would just add these together. And this is the sum of the squared errors. So it would just be this plus this, right? That's 800. But then you can probably imagine if I just keep adding for every record. So I only did that for the first and the second prediction. And how many predictions do we have in here? Number of predictions is, let's do length of pred. There's 133 predictions, so it's probably going to get bigger and bigger and bigger and kind of go to infinity. So sometimes we normalize that. So we take the mean of that. So the average of that. In this case, in two predictions, this would just look like these two predictions, and then we divide by 2. Sorry, where did I get my parenthesis off here? Oh, I already have them. There we go. So we would say that the average R squared value is 404 to that one. So that's why sometimes it will be, that's how you get this more normalized number, right? That's why we're not this kind of like very drastic number. And this is actually has it in a probability. I should look up the actual formula and calculation for this. I'll share that after. All right.
Is the R squared score, is that the same as the correlation?
Ooh, that is a good question. It is not going to be the same as the correlation. So the correlation is going to tell us, you're talking about this view here.
Yeah.
The correlation, which I probably shouldn't have even put this in here, so sorry, this fun little graph. This is only on the X data set. So this is only on the features. I did not put any Y labels in here. There's no, it doesn't actually know anything about anything other than these X features. So you can see age, sex, BMI, etc. Here's all our features. And then you'll see the same features again on this axis. And basically what it's looking at and saying is how much do these features move together? So as one feature goes up, does another feature also go up in accordance with that? Maybe if we look at kids, right? People under the age of like say 16 or 18, maybe their age has a high correlation with their height because kids get taller as they get older. So those are two variables that move together. They trend, they both trend upward in the same direction. Variables can also trend opposite each other. So as one goes up, the other one can go down as well. You think about as we progress into the winter, your AC bill goes down, but your furnace bill, your heat bill goes up, right? So they're inversely related to each other. They have a negative relationship on each other. So they still move together. They just move in opposite directions. Anyway, so that's what this correlation matrix represents. Everything that's like a closer to this one value means they move 100% kind of positively together. If you look diagonally down this matrix, they will all be ones because this is age and age, and this is sex and sex. We can't take these out of the graph, so just by the nature of plotting this. So just imagine this diagonal doesn't exist. All it's saying is it's 100% correlated with itself, which of course it is. It's the same data. So ignore that. But right here is an interesting one, right? So we have 0.9. Wow, that's a high degree of correlation. So this S2 is highly correlated to this S1. Let's go look what those are. Very high degree of correlation. So their total serum cholesterol is really highly correlated to their LDL number. And I don't really know why, because I'm not a doctor and will not pretend to be, but this is where you would really need like a business stakeholder. This is where you'd really need somebody who understands the data to explain this to you. And then on the opposite end of this spectrum, these really dark numbers, these are negative correlations. These are just as important as a positive correlation. Just like I said, furnace and AC, super related. So this S3 is really closely related to this S4, but they move in opposite directions. So S3 is the HDL and the TCH, the total cholesterol, and the high density lipoproteins work really kind of in opposite directions, which is interesting. Anything that hovers around 0, totally uncorrelated, at least in the data set that we have. We're not interested in these. The numbers closer to 0 are less insightful or less interesting in this way of visualizing the data. That was such a long-winded answer. I apologize. Basically, this would be, I classify it as exploratory data analysis. You would be looking at this information before you applied your model. Did I answer your question in maybe a long-winded way?
Yeah, that works.
Okay. Is there any other questions on that? Sorry, your question was, remind me, is this the same as, as R squared? So to close on that, in R squared, we're actually passing it our labels. So Y test is actually our true labels. What we really did observe for this person, this person, and this person for their diabetes progression numbers 1 year later. These are our actual observed values. So when we calculate our R squared, we're passing it we're passing the labels there, and then what we predicted those labels would be. So for R squared, it's actually kind of the very different from correlation because we're not passing it any X data. We're only passing it our Y and our Y hat. Whereas correlation, it's the opposite. We're not passing it any Y data. We're only passing it our X's. So here is our actual Y, and then this is our Y hat for pred. All right. Other questions? Okay, I will get a data set for you guys, and I will send it to you. I might have to curate it and or talk about feature engineering at our next discussion. Because one point, we're fortunate with this data set in that all of our input values, notice they're all numbers. Machine learning models need numbers, especially linear regression. Everything has to be in a numerical value. So if we have something like sex, notice here, they had sex, but these are all, they already did some prep work to make them numerical. So how did they get here and why do they look like that? That's something called feature engineering. So, typically you'll have a lot of not just numerical data, you'll have categorical data as well that you want to put into your model. So if we think about a house, it's got 3 bedrooms. Well, 3 is numerical. If we think about a house, what's a categorical variable for a house? Number of bedrooms would be numerical. What is it? Townhome. There we go. Type of house. There we go. Is it a townhome? Is it a single family residential? Is it a condo? Is it, you can have these different type of classes of a house. So what type of house is it? We're going to have to, those are not numbers. You cannot do condo times, times what? You can't multiply that with anything. And so we have to do something called feature engineering to transform that.
So Boolean would be like garage, true or false, right? So that'd be,
You hit the nail on the head. Yeah. So that's exactly, it's really not too, let's change you guys are going to say, well, yeah, that's obvious. So in the 4 minutes we have, all I'm going to say is if we have home type, and let's say we have a string that says condo, we have a string that says townhome, and we have a string that says single family. But we want to transform these into a way that our model can actually make a prediction. Again, machine learning models, they need numbers. They're not so smart. And so what we're going to do is exactly what you said. We're going to make a new column called condo, and we're going to say, does it exist or not? So it does exist for this record. This record doesn't say condo, so it's a 0. And this record doesn't say condo, so it's a 0. And then you come over here. We're going to do the same thing for townhome. And we're going to do the same thing for single family. So now you can see, imagine there's more data in here, and there's lots of things that say condo, so maybe, or single family or whatever. I'm just gonna put condo because it's shorter to write out. There we go. So this would look like this. Oh, sorry, those are zeros. My bad. There we are. So this is called one-hot encoding. Otherwise, that's the terminology that I see a lot in machine learning. If you come from more of the R world or statistics, you might hear these called something called dummy variables. But one-hot encoding. So basically you're saying you're taking labeled values and you're turning them into binary columns. So if this had, it brings up an interesting, oh good, I have 2 more minutes, okay. I must be going very fast. It brings up an interesting thing, which is how many labels are in here. So if we have, in this case, we have 3 labels, but what if we had 10 labels or 10,000 labels? That is something called the cardinality of a column. And so the cardinality, how many labels do we, unique labels do we have in a data set? In this case, it's 3. But if we had, say, 10,000 unique labels and we did one-hot encoding, your data set just went from 1 column to 10,000 columns. So that's something to just be aware of. Sometimes we apply strategies to mitigate that, but it expands this. So now your data set may look a lot bigger. But we have to do this because the machine doesn't know how to read these. It has to be in numerical values. Another way we could have done this is we could have labeled this 1, all condos are 1, all townhomes are 2, all single families are 3. But remember when we talked earlier about that's telling the model that a townhome is twice as much as a condo and a single family is twice as much or 3 times as much as a condo. So that's why you have to do one-hot encoding. When you don't have something, and I'll do a whole thing on feature engineering, so, but you have to do one-hot encoding when you don't have something called an ordinal variable. So this is something called a nominal variable. Nominal, meaning no order. No order exists in this. One is not greater than the other. An ordinal variable might be something like education. There's an order to it. The word order is kind of in this variable. So first you get your high school, and then you get your college, and then you get your master's, and then you get your PhD. There's typically an order of progression to this. So this would be considered an ordinal number. So you could go 1, 2, 3, 4. It doesn't, is PhD 4 times more than high school? No, not really, doesn't really make sense, but there is an order that those progress to. So it makes a little more sense for that than it does for this situation here. Okay, thanks. That was my 5 minutes on feature engineering. We'll do more on that. I like to just throw a lot of stuff at you guys at the very end of class. I'm sure you love that. Thank you guys. I appreciate it. And we do not go on Wednesday. Valentine's Day. Enjoy your time off. I'll send a video.
Is there, next Monday is President's Day?
Oh, thank you so much. I'll drop in the chat too. do not come President's Day, and there is no lecture, no video. So you get a free day off. I talked with Nate about that. So don't show up. Nothing to do Monday.
So no
All right,
homework.
cool.
I'll send the details in the
Okay.
chat. All right. Bye, guys.
Thanks.
Thank you.
Thank you.